Hey, this is Kevin, and today we'll be doing Leetcode number 242, Valid Anagram. This is labeled as an easy problem. So the goal of the valid anagram problem is given two strings S and T, return true if T is an anagram of S and false otherwise. If you're not familiar, an anagram is a word or phrase formed by rearranging the letters of a different word or phrase, typically using all the original letters exactly once. And the constraints that they provide are that the lengths of both strings are between 1 and 5,000, and they are made of lowercase English letters. So the first example is anagram, and the word anagram, but with the N and A switched. So it's very clear that these are made up of the same letters, so they are anagrams of each other. So the output is true. In the second example, we have two strings, rat and car, and these are not anagrams because rat doesn't have a C and car doesn't have a T. So the output is false. So how do you solve something like this? Well, how do you code a anagram detector function? Well, the first thing that comes to my mind is just keep track of how many times each letter appears in each string, right? So, for example, in anagram, let's look for the letter A. It appears 1, 2, 3 times. And T, A appears 1, 2, 3 times. And you can kind of play the game of like canceling them out until you're left with nothing or you're left with differences. And that might be one approach. But how can we actually do this? Well, we can use a data structure that we've seen before. This is called a dictionary or hashmap. And it's basically a data structure that is able to store key value pairs. For example, John is stored in name, 19 is stored in age, male is stored in gender. But how do we use this for this specific problem? Well, we could actually have a hash map where we have the keys be the letters and the values be the frequency that the letter appears. So A would appear 3 times, B would appear 0 times, and C would appear 0 times in anagram. And we can actually use this to make a pretty efficient solution. So this is the code here, but don't focus on that too much yet. I'm going to go step through how the code actually works. So lines 3 to 4 of this code is basically an early return. So I have this condition if len s is not equal to len t, then return false. Because any anagrams or any words that are anagram of other words must be the same exact length. You cannot have an anagram of two different strings that are different lengths, because once you run out of letters in one string, there's no way they can be equal. And in lines 6 and 7, I initialize two hash maps. So I named one count s, and this is going to count, keep track of the letters in the string s, and count t will keep track of the letters in string t. So lines 9 through 11 is the main loop for filling these tables, these hash maps, with letters of key and value. So let's do that right now. So step 9, for index in range len of s, count s index equals count s dot get. So dot get here, if you try to call, say in count s right now, we want to see if we have the letter A already in there. So we try to call count s bracket A. That would return an error because currently the hash map is empty. So we using .get, if it's empty, we can set it to an initial value of 0, which is that second argument right there. So we run this code and we get A is the first letter of S, which is 1, and T has the first letter of N. So those are added as keys, and the value is incremented by 1 from the default value of 0. And now we move on. So 12 to 14 is not going to run yet because we're still currently in the range of length of S. So we go on to the second character, so N and A, and these are both new for both strings, so added. And when we move on again, A is already in the hash map. So instead of creating a new key value, it increments the existing value of the key A. So we can go through this a couple more times, and then we have finished incrementing all the characters. So now we have an accurate count of how many characters are in S and how many characters are in T, and also what specific characters are used and their frequencies. And now it's time to compare these two hash maps. So line 12 through 14 is the code to do that. So for character in count S, so we start with the first character, and it's an A in keys. And so we find A in count T hash map, and we compare the values. And 3 equals 3, so that's fine. But if we find a single value that does not equal, then we can return false early because we can tell that it's not an anagram, it's not valid. But if, for example, in this one, everything checks out, then we can return true at the end of the program. So S and T in this case, with these inputs, are a valid anagram. But let's step through this with example 2, which we already know is not an anagram. So we add the letters. In this case, there's only one of each, and there's only 3 letters, so it's pretty fast. And now we start comparing. We find the R, there's one of each. We find the A, there's one of each. And now, when we try to find T, which is a value of 1 in S, we call T, we look for T in count T. And because there's no T found, it creates a 0. So 1 does not equal 0. So it triggers the return function of returning false. So the end result, the output, is that that is not a valid anagram of car. So this is the solution in full. And I'm going to talk a little bit about the time complexity. So the time complexity can be generalized to ON, just because we only need to iterate through the strings once. So if you want to be more specific, it depends on the length of the strings, S and T. So it would just be S plus T. And spacing complexity is also generalized ON, because we are creating a hash map for each string, And the worst case is that both strings have totally unique characters, and we need to, have space for every single character. But yeah, so ON for both time and space. But there's a different way that you can use, and this can be a bit difficult to think about if you haven't heard of this methods, but you can actually pre-process the strings first. So if you sort them by alphabetical order, then compare the strings, they are either exactly equal or they cannot be anagrams. And the reason that works is because there's only 26 letters, and each one has a designated order. So even if you have duplicates of a letter, say the triple A here, all the A's have to be before the B's and before the C's. And if you don't have a matching pair, that means there's a difference in the letter collection. And so it's an invalid anagram. So you can see here example 1 turns into A, G, M, N, I. And sorting the T will give you the same exact result. While sorting the second example, you can see from AR and AC that these are clearly not anagrams, because even though the second string does have an R, the R position should be in the second one to even be an anagram. So it's a very quick detection. So this is the code. It's a lot shorter. It's literally like one condition, and you return true if they're exactly equal, and if they're not, then it breaks early and it returns false. So the time and space complexity for this is largely dependent on the sorting method you use. So some sorting method works better than others. I just use the sorted method from Python, which is built in. So you can see here I put the string in the sorted call, and the time complexity for this, I looked it up, it's O n log n, and the space complexity ranges from best case O1 constant to ON depending on the usage. And that's a lot of stuff under the hood, but as you can see here from the implementation, it's slightly faster and slightly more efficient than the previous method of using hash maps. And that is valid anagram.